Okay, so let's go ahead and get started on the limit definition of a derivative, part 3. The first time we talked about more the conceptual backdrop and did one example. The next time we did some very remedial examples, very straightforward in terms of their form. We want to sort of venture out and start doing a few examples that are a little bit more difficult. And let's go ahead and jump right in. And instead of root x, let's call f of x 2 times root x minus 2. Okay? Now, obviously, f of x plus h is equal to 2. And as I was saying before, if you want to check yourself, go ahead and pause at any point and see whether you can actually do this on your own. And then, restart and see whether you got it right, or see whether I'm wrong. Doesn't happen very often, but I stumbled upon that T-shirt a little bit too late, the one that they advertise on Facebook that says, "I'm a math teacher. Let's just assume that I'm never wrong." Of course, we all know that that's not exactly the case, but amusing to me nonetheless. So that is f of x plus h minus f of x, all of that over h. Now, is there a way to clean this up a little bit? And the answer, thankfully, is yes. Now remember, when we're dealing with limits, you can always pull a constant out in front. And since the 2 is common to the numerator, you actually can pull it out in front, okay? At which point, it's not going to be quite as messy when you multiply by the conjugate. Okay, that way the 2 is kind of out of the way and it doesn't cause any notational snafus. Excuse me. And so we have 2 times the limit as h approaches 0 of x plus h minus 2 minus, that's supposed to be, minus 2. My bad. And that's supposed to be minus 2 as well. I guess I got distracted by the plus h, okay? Now, let's go ahead and say h, and then we'll put a bracket to make sure that we're all kosher in terms of our notation. Okay, now when we distribute that negative in the numerator, it's going to give us x plus h minus 2 minus x plus 2. So what's going to happen is that numerator is going to wind up simplifying just the plain old h. And we have x plus h minus 2 plus x minus 2. Okay, remember the very common mistake of not carrying this denominator down to the next step and joining it with the h. So when h winds up canceling out, and I wind up just getting a 1 as a factor in the numerator, when I plug in down here, I'm going to get 2 over 2 times x minus 2, right? Because when the h gets plugged in, that just turns into root x minus 2, and when you add something to itself, there are 2 of them, which winds up being 1 over rad x minus 2. And that is the derivative of this original function right here. So if I wanted to know the slope of this function at 6, okay, I could actually say, well, the slope function evaluated at 6 is 1 over root 6 minus 2, or 1 over root 4, which is 1/2. The slope of this function at 6 is the derivative function evaluated at that particular value. Okay, well that's kind of fun. Let's go ahead and move on to one that's actually multiple terms. Now, you kind of go, oh my gosh, multiple terms? That might be a little bit tricky. But in the end, it actually winds up being very easy. Because remember that you can do limits term by term. Now in this case you don't really have to. I mean, this one actually isn't all that difficult. It's just a matter of not being sloppy with your notation and actually, tracking everything and keeping track of everything. So let's go ahead and actually simplify f of x plus h when we put it up here in the numerator. It actually winds up being x squared plus 2xh plus h squared minus x minus h minus x squared minus x. Okay, so that's my f of x plus h right here. That's my f of x. And when I start actually simplifying, okay, I know that once this negative right here gets distributed, this x squared and this x squared, this x and this x, they're all going to go bye-bye. And just like what happened last video when I was dealing with a polynomial, right, the only thing that is left in the numerator are terms that have h, and therefore they have a common factor. I can factor it out, at which point the h's cancel. I'm left with the limit as h approaches 0 of 2x plus h minus 1, and that is simply 2x minus 1. Okay, let's go ahead and do a rational function, more specifically a reciprocal function, since those are relatively straightforward. Okay, now if we were to be given something that was a little bit amiss, let's say that we were, instead of being given that, let's say that we were given f of x is equal to 2x over x minus 3 or something like that. Well, I mean, my advice to you on this would actually be, if you're doing it, if you have to do it by limit definition, which of course would be nasty in this form, go ahead and do the division, right? Go ahead and turn that into 2x minus 6 plus 6 so that you can actually pull apart the fraction and actually get that, okay? And then just do the derivative term by term. Now, of course, you should remember that the derivative, meaning the slope of a constant term, is 0. So really, in the end, the derivative of this function is really the derivative of what's left once you turn it into a reciprocal function by actually accomplishing the division. Now, of course, you can do it this way, or you can actually, x minus 3 goes into 2x, blah, 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 sort of the polynomial long division. I prefer this when we're just dealing with linears because it actually winds up being much, much easier. You just pull it apart and simplify. But let's go ahead and do one that's a little bit easier than that, but of course of the same variety as what you would eventually get that way. And we have 2 over x plus h plus 3. Now, the only thing that winds up being difficult about this is the number of terms that are a part of this complex fraction the moment that I set up the limit definition. But it's not really all that hard. It's just tedious and detail-oriented, right? So there's nothing conceptually that difficult about this. It's just somewhat burdensome to be able to keep track of all of the terms, right? But of course, this is just another complex fraction that needs to be simplified. In order to simplify it, I multiply through by what would have been the common denominator in the big numerator had I actually, gone to the trouble of finding it. But I know from practice, and because, my former math teacher was nice enough to tell me, you can actually just multiply through by what would have been the common denominator, and you wind up getting something much, much easier. Now, in order to get to the next one, I'm also going to factor out that 2. That 2 I'm going to pull out in front, which is why I'm going to go ahead and not include that 2 when I start simplifying this expression that we're taking the limit of, okay? So that 2 was a common factor of both terms in the big numerator, and so I just pulled it out in front, okay? Now, I have multiplied through, and again, I cannot emphasize enough the fact that you cannot lose that denominator. That needs to come on over here and join the h in this big denominator. Now, when I distribute that negative across the x plus h plus 3, the x and the 3, all of it's going to change sign, but, in terms of canceling out, the x and the 3 are going to change sign. all that's going to be left in that numerator is going to be an h, in fact a negative h, right? And so when I get to this stage right here, I just need to cancel that out, make sure that I don't lose the negative in the process, and I wind up with 2 times negative 1 over x plus 3 squared, or negative 2 over x plus 3 squared. That is the derivative of your original function. If you want to know what the slope of this function is at any value of x, it's relatively easy once you have this. This will tell you, okay? Now the last one that I want to do is going to probably make some of your stomachs turn, because the moment that I mention trig, some of y'all start to break out into hives and even go into, you know, anaphylactic shock. But we have to deal with trig. Okay, if you are not keeping up with your unit circle values and your trig IDs, you are going to be in a world of hurt come May, okay? I don't care if you're actually required to do it for class. There are some things, and I probably do a video on this, the things that are not calculus related but will be incredibly beneficial if you keep up with in an ongoing way, okay? Now, I know that the derivative is the limit as h approaches 0 of sine x plus h minus sine x, all of that, over h. But this isn't a polynomial, so all of a sudden I'm lost. Except I seem to remember that there's an identity for that, isn't there? An identity called the sum and difference identity. Okay, and I get sine x cosine h minus plus cosine x sine h minus sine x, all of that over h. Now, we need to go ahead and just move things around a little bit. And if we move things around a little bit, I think that you're going to wind up understanding where we're going to go with this. Okay? I'm going to pull this third term, and I'm going to pull it over here next to this one, and then factor out the sine x. And when I do that, I get that. And then I'm going to go ahead and pull out that cosine x. Okay, so I've mixed up the order of the numerator terms and then separated fractions and rewritten it just to suit my purposes. Now, this as h goes to 0 and this as h goes to 0 should be very, very familiar. This goes to 0. This goes to 1 when I actually evaluate it as h goes to 0. So this whole term falls out because that portion of it right here is going to 0. This portion of it is going to 1, and therefore the derivative of sine is cosine. Okay? And some of you may remember that from when we actually did a few things in terms of taking the derivative at the end of last year. And I think I may have even done this on the board, but now you have it for, you know, all time. You can access it anytime you want. In the next video, I think I'm going to do a couple of more nasty examples, and then I'm going to introduce what's called the alternate definition of the derivative, which is pretty important for when we actually get to the AP exam, because when we get to the AP exam, you won't be asked to actually do this process. You'll be asked to look at something, look at a limit that is given to you, and automatically know that it represents the limit definition of a particular derivative. And therefore, we're going to go ahead and do that towards the end of the next one. Okay? Let's go ahead and call it quits on video number 3 on the the limit definition of a derivative, and I'll start number 4 here in just a second. But I hope that that clears things up and helps you out with a couple of a little bit more robust examples of how to actually execute problems of this variety. Okay?